Hey guys, this video is going to be about metal-phosphine bonding at an undergraduate level. Well, what actually is a phosphine ligand? Well, strictly phosphine is pH 3, however inorganic chemists generally refer to most substituted phosphines as phosphines. So PR3 is the general formula we can give this, however that may be something like PME3, PET3, PPH3, and so on, maybe even some chelating ligands such as PH2P, PH2. But they act as sigma donors and pi acceptors. So let's actually look at the bonding. Well, first of all is sigma bonding, a bit like carbonyl bonding. We can have a central metal like this. There'll be some d orbitals that may look a bit like this, depending on the axes. So this could be the x squared minus y squared, as we've got the different lobes of different shades. Let's put some axes up here. So let's say this is y and this is x, so dx squared minus y squared, and then we'll have our phosphine here, and let's say our 3R, so PR3, our generic one, and then we can have a lone pair in an orbital, say a bit like this, and then our lone pair, as per a normal sigma bond, we can have some overlap here, forming a nice sigma bond, but because it's a lone pair in here, it's a coordinate bond. So another way we may draw this is just simply as such. However, as I said previously, the metal to phosphorus bond is not just sigma, we also have to consider the pi bonding, the pi back bonding, to be more specific. So if we look at this, once again we can have our metal. However, this time we can have, let's say, an xy orbital, dxy, something like this, shade in those lobes. They can be black and white or plus and minus, depending which you prefer. Then we're going to have our phosphorus here. We've got our coordinate sigma bond that we've already talked about, as it's PR3 as a generic way to say it, draw that in. However, this time, now we want to have a look at an empty orbital. We can get pi back bonding into an empty, keyword being empty orbital. Now, I would tell you which orbital it is, however, research hasn't quite figured that out 100%. There's still debate among the scientific community. Originally they thought maybe it was some d orbitals on the phosphorus that was partaking in the back bonding, however, that's been disproven, and there's some people thinking it's p orbital, some people thinking this, that and the other. So no one actually knows for sure, but what we do know is it's an empty orbital, and because we have electron density on that metal, it can back bond to an empty orbital on that phosphorus. So again, that is the pi back bonding. And now in blue, just to remind you, that's our sigma bonding. Now, as you can see, the metal to phosphorus bond is a function of these two things. So we can actually look at the different sigma donating ability and the pi accepting ability of all different PR3 ligands. Well, as we can see, we've got some trends here, but why? Why do we have these trends? Well, let's take PF3 for example. Let's talk about why is this a bad sigma donor. So you may already be able to see this, but we have some electronegativities in play. Fluorine is very electronegative, one of the most electronegative atoms there. And because of that, it will pull electron density away from that phosphorus. And as we've got a lone pair here, you may think it's held in a particular orbital, but as you may know from molecular orbital theory and things like that, everything's kind of spread around a little bit. It's localized to one area, but there's a certain percentage that it will be in an area and other times it's not. So that electron density can be pulled away, therefore it's no longer a good sigma donor. And the other thing we can look at is the reverse. Let's say take PME3. Well, as you know, we can get something called the inductive effect or hyperconjugation, whichever you prefer, and because of that, it can put electron density onto that phosphorus. So now, suddenly, we have more electron density, meaning that it's more likely to form a coordinate bond to a metal. Why is this important, you may ask? Well, when we're looking at things like pi acceptability as well, if we have a metal with a large electron density on it, so we have lots of electrons in those d orbitals, or we can get very, very strong pi back bonding to these ligands, increasing that bond strength. Whereas if we have a electron poor complex, it's going to favour this sigma donating ability because it's going to want more electron density and it can stabilise that quite easily. Hopefully that makes sense and you found that video helpful. Please share it with your friends if they may find it helpful. Subscribe for more and like so I know you found this video helpful. Thank you.